The cube stands as the ultimate symbol of rigid, predictable geometry. It is a shape defined by flat faces, straight edges, and fixed right angles. But if you balance that standard block on one of its tips, the longest diagonal vertex, you unlock a different kind of physical behavior. When you spin the block rapidly on this axis, the sharp corners disappear and the straight edges blur into a smooth, continuous solid. At the top and bottom of this new volume, we see exactly what we expect: two perfectly symmetrical, solid cones swept out by the rotating vertices. The anomaly appears in the middle. Instead of a thick cylinder, the spinning block creates a smooth, curved surface with a pinched, wasp-waisted center. This creates a geometric mystery. How can an object built entirely of rigid, straight edges produce an elegantly curved shape merely by spinning? To solve the mystery, we have to move past physical intuition and use digital modeling to freeze the cube's rotation and examine its internal anatomy. We can see that the upper and lower vertices rotate in tight, fixed circles around the vertical axis, naturally creating the top and bottom cones. This diagram tracks the cube's edges. Isolating the 6 middle edges, we see how they move. They never intersect the central axis, nor are they parallel to it. In geometry, this unique relationship defines them as skew lines. The curved middle is the literal physical surface swept out by these straight skew lines as they travel through the air. This sweeping curve has a specific mathematical name, a double-ruled, one-sheeted hyperboloid. While the shape looks complex, mapping it doesn't require advanced calculus. It can be fully defined using standard secondary school mathematics. This chart labels the cube's vertices and notes the specific skew angles. By identifying these basic internal angles, we can calculate the precise path the rotating lines must take. Using these angles and familiar tools like the law of cosines and the Pythagorean theorem, we can build a geometric equation for every point on the surface. As this technical model shows, the resulting algebraic equation creates a boundary that perfectly dictates the limits of the hyperboloid surface. Ultimately, these complex algebraic equations represent the literal physical movement of the cube's straight edges through 3D space. We can see the results of that math here, moving from the static yellow cube on the left to the complex 3D printed hyperboloid on the right. Introducing the equation for a one-sheeted hyperboloid on a chalkboard often feels abstract and intimidating to students. Using a physical model creates a multimodal experience where play builds a natural intuition for the geometry before the math is ever introduced. This progression, moving from tactile play to digital modeling and finally to algebraic verification, is the foundation of mathematical modeling. A curious mindset motivates a student to investigate the mechanics of a shape rather than simply memorizing formulas for a test. Mathematics is a creative tool that allows us to playfully interact with the universe to uncover the hidden artistic structures within it.